as the James Webb Telescope has just observed artificial light on the planet Proxima B. This marks a groundbreaking discovery. The JWST MIRI instrument is capable of detecting large artificial light sources on distant planets. This is the first real evidence of a technosignature indicating the presence of intelligent life forms on another planet. MIRI, a high-resolution infrared instrument, is extremely sensitive to infrared radiation. It can detect distant metropolis cities and industrial facilities at vast distances. This capability extends not only to our neighboring system Proxima Centauri, but MIRI can detect artificial light sources and potential alien cities throughout the known universe. It sounds fantastic what we can do with our new super telescopes on Earth or from near-Earth space. We can now easily detect large settlements within the known universe. We have already achieved a masterpiece with the MIRI spectrometer at the JWST, and there is even more to come. Another megatelescope will be launched in Chile in 2028, the Extremely Large Telescope, ELT, with a 39 main mirror. This telescope will look deeper and sharper into space than ever before. We need these technical innovations because our thirst for knowledge about the universe is far from quenched. We are only at the beginning of exploring distant worlds, and we need instruments like the JWST and the ELT to examine exoplanets for traces of life. In addition to the ability to detect artificial light emanating from gigantic cities in space or extraterrestrial airfields, we will soon be using a new secret weapon with the ELT system. We will be able to detect traces of vegetation on distant planets. The development will go on in our search for other species in space. We will use more and better instruments and tools until we have found and made contact with other life forms. The first artificial light source on Proxima B is a moment scientists have long dreamed of. For the first time, they are using a telescope to look so precisely into our neighboring star system that places of life become visible to us. An artificial light source on the planet Proxima B reveals the presence of technology and therefore also of some form of advanced life. It sounds crazy, but the JWST could even analyze our own activities on Earth based on our light signatures. The best telescopes of all time would easily capture the lights of major cities such as New York, Rio de Janeiro, or Beijing. With its fine sensors, it can filter out the artificial light tracks of airports, large industrial plants, or even space stations from the natural light emissions of the Earth. The same is happening on Proxima B. For the first time, we will have precise analyses in our hands of where life is located, how much artificial light it produces, and how mechanized the species is likely to be. We have thus made a quantum leap in our search for life in space, and one day we will certainly have the technical means to communicate with other civilizations. If we wanted to send messages to Proxima B, they would take more than 4 years to travel one way by normal means. We would have to wait another 4 years for a reply to come back. All hopes are currently pinned on the development of the first quantum computers. Quantum communications know neither a fixed place nor a fixed time. Once we have cracked this fantastic technology, we will develop quantum means of communication and communicate with distant civilizations as if in real time. Does that sound like pure utopia to you? Then hold on tight because utopias often become truths very, very quickly. It was 2016 and a long way from the now very real era of James Webb when scientists dreamed of exploring alien worlds. Back then, a groundbreaking simulation predicted how the James Webb Space Telescope would study the surface of the exoplanet Proxima B in an unknown future. These simulations aimed to analyze the planet's atmospheric and thermal properties. By 2016, researchers were already dreaming of finding out whether Proxima B had an atmosphere that was potentially hospitable to life. What was utopia less than 10 years ago is now reality. At that time, simulations of Proxima B's unique orbit already showed that the highly interesting exoplanet lies within the habitable zone of its parent star, Proxima Centauri. The JWST will carry out regular and comprehensive observations of the day and night sides of Proxima B. This planet orbits its star in a bound manner, just as our moon orbits us. Proxima B always has the same side facing its star, and one side is always in shadow. Reconstructions have shown that there must be extreme temperature differences between the day and night sides of Proxima B. Unless the planet has an atmosphere that redistributes heat, without an atmosphere, the day side would be blazing hot and the night side icy cold. The presence of an atmosphere, on the other hand, would allow heat to be distributed more evenly. This is exactly what we can now find out thanks to the JWST. The 2016 simulations showed even more. There could be a tempered strip in the border areas between the day and night sides. It sounds strange to imagine that civilizations exist on a planet that is half light and half dark, and that these beings settled on a strip that is perhaps several thousand kilometers wide around the globe. But it is possible. We need to keep opening our horizons and possibilities in the search for other life forms in space. To be really sure, we need real analysis. In 2016, the exact analysis of the chemical composition of the atmosphere of Proxima B was still a dream. Today, the JWST proves its ingenuity every day and shows us exact analysis profiles for worlds that are sometimes hundreds or even thousands of light-years away. The JWST can recognize signatures of water, carbon dioxide, and methane, and has already made finds. The last comprehensive profile was obtained from the exoplanet K218b, where the JWST found evidence of 4 biomarkers in the atmosphere. The more such biosignatures are measured around a planet, the more likely it is that life could exist there. Particularly exciting is the potential discovery of ozone, which is considered a strong indicator of biological activity because it is predominantly produced by biological processes in our atmosphere. K218b could therefore be an inhabited world. However, we have not yet found any traces of artificial light there. This planet could be a pure water world, but that does not mean that it is uninhabited. We have to take into account that there is intelligent life in the water, possibly even cities, and we have to consider that not all developed species have artificial light. We haven't had the light bulb for that long, and yet humans were already intelligent and to a certain extent mechanized in ancient times. The JWST detects PL growth on Proxima B. The James Webb Space Telescope, or JWST, is primarily designed to observe the universe in the infrared range and carry out detailed spectral analyses of distant celestial bodies. What the JWST has not yet proven is its ability to detect plant growth on exoplanets, but it does have the potential to do this. In our search for life in space, we must not only rely on technosignatures and the emissions of highly advanced species. We must also look for planets that may only have plants and animals or other simpler life forms. The JWST can provide indirect evidence of plant growth by analyzing atmospheric constituents and reflected light spectra. Scientists call this technique vegetation red edge, VRE, spectroscopy. These are spectral signatures created by the reflective properties of plants in the near-infrared range. When light passes through the atmosphere of an exoplanet and is reflected by the surface, specific patterns in the reflected light could indicate the presence of chlorophyll or other photosynthetic pigments. The detection of such signatures is still very challenging. The detection of VRE requires extremely precise measurements and high resolution, which can be affected by the exoplanet's atmospheric disturbances and the signal-to-noise ratio. Although the JWST is designed for such measurements, we are now beginning to utilize these capabilities, and researchers are certainly getting better at finding and detecting traces of life in space. We are living in exciting times because the JWST has started a revolution in space exploration, and this development continues. Direct detection of plant growth or biological activity will require future telescopes and missions specifically designed to search for biosignatures. One example is the planned LUVOIR telescope, Large UV/Optical/IR Surveyor, and this future space telescope aims, among other things, to examine the atmospheric properties of exoplanets with even greater precision and to detect potential biosignatures such as the VRE. Another important telescope currently under development is the Habitable Exoplanet Imaging Mission, or HABEX for short, which will take the first direct images of Earth-like exoplanets and analyze their atmospheres. Recent observations by the James Webb Space Telescope, JWST, have unveiled a remarkable discovery: the detection of artificial light on Proxima B, a potentially habitable exoplanet orbiting Proxima Centauri. This breakthrough marks a significant milestone in the search for extraterrestrial intelligence. Equipped with its MIRI instrument, JWST demonstrated its capability to discern large-scale artificial light sources across vast distances. This technological feat provides compelling evidence of a technosignature, hinting at the presence of advanced civilizations beyond Earth. MIRI, the high-resolution infrared instrument on JWST, operates with exceptional sensitivity to infrared radiation. Its capability extends beyond our local cosmic neighborhood, offering the potential to detect artificial light sources and possibly even urban centers on exoplanets throughout the universe. This advanced capability positions JWST as a pioneering tool in the exploration of distant worlds and the quest for signs of life beyond our solar system. Looking forward, the astronomical community anticipates further advancements with the deployment of the Extremely Large Telescope, ELT, in Chile, scheduled for 2028. Boasting a 39 main mirror, ELT promises unprecedented clarity and depth in observing cosmic phenomena. This next-generation telescope aims to surpass current observational limits, offering enhanced capabilities for studying exoplanetary atmospheres and potential biosignatures. The pursuit of understanding distant worlds and potential extraterrestrial life forms remains a central focus of modern astronomy. Instruments like JWST and future telescopes such as ELT are pivotal in this endeavor, enabling detailed analyses of exoplanetary conditions and environments. The development of new technologies, including quantum computing and advanced space-based observatories, holds the promise of revolutionizing our ability to explore and communicate with civilizations beyond Earth. The discovery of artificial light on Proxima B underscores the transformative impact of space telescopes in unlocking the mysteries of the cosmos. These telescopes not only expand our knowledge of distant planets and their atmospheric compositions, but also pave the way for potentially groundbreaking discoveries in astrobiology. By detecting technosignatures and analyzing spectral data, astronomers can infer the presence of advanced civilizations and gain insights into their technological capabilities. Moreover, the capability to detect and analyze vegetation on distant exoplanets represents another frontier in space exploration. Techniques such as vegetation red edge, VRE, spectroscopy, employed by JWST and future observatories like LUVOIR and HABEX, offer avenues to identify biosignatures indicative of plant life. These advanced instruments aim to characterize exoplanetary atmospheres with unprecedented precision, potentially revealing Earth-like environments capable of supporting biological activity. The search for life beyond Earth is fueled by the collaborative efforts of scientists and engineers worldwide. It involves not only the advancement of observational technologies, but also the development of theoretical models and computational tools to interpret complex astronomical data. The synergy between observational data from telescopes like JWST and theoretical frameworks helps refine our understanding of planetary formation, habitability zones, and the potential for life in the universe. As we continue to explore the cosmos, each discovery brings us closer to answering profound questions about our place in the universe and the existence of extraterrestrial life. The quest to detect and understand artificial light sources, vegetation, and other potential indicators of life on exoplanets represents a crucial step forward in astrobiology. It challenges us to expand our perspectives and embrace the possibility of encountering civilizations beyond our own. In conclusion, the detection of artificial light on Proxima B by JWST highlights the transformative impact of space exploration. It underscores the capabilities of modern telescopes to reveal new insights into the universe's diversity and complexity. With ongoing advancements in observational technology and theoretical understanding, we are poised to uncover more secrets of distant worlds and potentially establish contact with intelligent civilizations beyond Earth. The journey of discovery continues, driven by humanity's enduring curiosity and quest for knowledge in the cosmos.